8.2.4 Principal Irreversibilities and Losses. The processes of an actual vapor power cycle are different from those of the ideal Rankine cycle because of the irreversibilities. The irreversibilities are present in each of the four components in the actual vapor power cycles. There may be pressure drop in the condenser and the boiler due to the fluid friction. There may be heat loss to the surroundings, but these are considered relatively small irreversibilities. We are going to take a look at the major irreversibilities associated with the pump and the turbine. Previously, we assumed the isentropic processes in the pump and the turbine for the ideal Rankine cycle, but the actual pump may require a greater work input, and the actual turbine produces a smaller work output due to the irreversibilities. The isentropic efficiencies are defined to compare the performance of the actual devices to the ideal devices. Let's see the processes on a TS diagram. The largest deviation between the actual process and the ideal process come from the turbine. The solid line shows the ideal processes. The dashed line shows the actual processes. We can see the actual cycle deviates from the ideal cycle. Process 1-2S is an isentropic process. It is a vertical line. The actual process will end up at state 2 with a larger entropy value due to the irreversibility. The irreversibilities will result in smaller work output compared to the isentropic process at the given operating conditions. In a pump, the irreversibilities and energy loss are similar to the ones in the turbine. The working fluid flow across the pump accompanies irreversibilities. The irreversibilities from the pump is much smaller, as the associated work with the pump is small. Process 3-4S is an isentropic process. It is represented as a vertical line. The actual process will go through process 3-4 with a larger entropy value. The actual work input to compress the fluid from low pressure at state 3 to high pressure at state 4 is greater. Example 8.2. Reconsider the vapor power cycle of example 8.1, but include in the analysis that the turbine and the pump each have an isentropic efficiency of 85%. Determine for the modified cycle the thermal efficiency, mass flow rate of the steam for a net power output of 100 MPa. The rate of heat transfer Q dot into the working fluid as it passes through the boiler. The rate of heat transfer Q dot out from the condensing steam as it passes through the condenser. The mass flow rate of the condenser cooling water if the cooling water enters the condenser at 15 degrees Celsius and exits at 35 degrees Celsius. This question is almost the same as example 8.1. The only difference is that in this problem, the turbine and the pump accompany irreversibilities. They don't follow the isentropic process. We are going to determine the actual state using the isentropic efficiencies. So this is the state property we created in example 8.1. The process 1, 2, and 3, 4 are isentropic processes. So the properties we acquired in the previous example are for the isentropic processes. So the table at the bottom, I've added the actual state 2 and 4 in the new table. So we are going to determine the enthalpy for the actual processes. enthalpy at state 2 and enthalpy at state 4. And the enthalpy we calculated in previous examples are for the isentropic processes. Let's first determine H2. The isentropic efficiency of a turbine is given. It's 0.85, and which is defined. So H2 is the enthalpy for the actual process. H2S is the enthalpy for the isentropic process. So we are going to solve it for H2. So the H2 for the actual process is 1939.3. Next, let's find H4. The pump work is expressed H4 minus H3 from the energy balance. And pump work for isentropic process can be expressed V3 times P4 minus P3. Recall that this was derived for the isentropic pump. Actual pump work may be written as isentropic pump work divided by isentropic efficiency of a pump. And substitute this into here. H4 can be written so we calculate H4, enthalpy for the actual process. So H4 is 183.36 kilojoule per kilogram. So now we got H2 and H4 for the actual processes. The remainder of the question is quite the same as example 8.1. We'll just solve the first part of the question. Determine the thermal efficiency of the cycle. So we are going to use the updated table with new H2 and H4. The thermal efficiency of the cycle can be expressed in terms of enthalpy. So we got the new H2 and H4 values. The thermal efficiency of an actual vapor cycle is 31.4%. And previously we got 37.1% from the ideal Rankine cycle in example 8.1. So the actual vapor cycle has a lower thermal efficiency.